Let me welcome you to this lecture. We have now discussed the chemistry of metal olefin as well as metal diolefin complexes, and we have looked at the bonding as well as structure of these metal diolefin complexes. So let us now discuss about another type of pi complex, that is metal enil complexes. Now, enil ligand is a class of ligand with formula CnHn plus 2. So these are with an odd number of carbon atom. This n is always going to be an odd number, and these ligands essentially can be considered as ligands containing as neutral ligands with odd number of pi electrons, and we can also consider them as either anionic or cationic ligands with even number of pi electrons. So examples of enil ligand, or the simplest enil ligand that we can write, is containing 3 carbon atom, and if we have a pi cloud over there, that contains, if we consider it to be a neutral ligand, that is a neutral allyl radical, then it is a 3 electron donor and it can bind to metal centers. So this is allyl ligand, that is enil ligand containing 3 carbon atom, or the simplest of the enil ligand. So this ligand can bind to metal centers in this fashion, and it is a 3 electron donor. So it is now, and it binds to metal centers in eta 3 fashion, that is all 3 carbon atoms are considered to be bonded to the metal center. Now we can have other enil ligands as well, apart from when n is equal to 3, we can have n equal to 5. So then we will have pentadienyl ligand. So this is pentadienyl ligand, and this can bind to metal centers in this eta 5 coordination mode, and this, if we consider it to be a neutral ligand, then it is a 5 electron donor, and if we consider it to be an anionic ligand, then it is a 6 electron donor. Similarly, the allyl ligand will be a 4 electron donor if we consider the ligand to be anionic. So these are the enil. We can have more number of carbon atoms as well. So that is going to be, say, cycloheptatrienyl and more complex enil ligands containing higher number of odd carbon atoms with odd number of carbon atoms in them. So during this lecture we will discuss about we will focus on allyl ligand, or we will discuss about the preparation of allyl complexes. So preparation of allyl complexes essentially, or all the methods for preparation of allyl complexes can be essentially categorized into 3 different classes of reactions. In the first case, the first one is the metathesis reaction, where you substitute a ligand X by eta 3 allyl ligand. So these are the simplest. This is the simplest way to prepare a metal allyl complex. You can take a metal complex with a labile ligand and then substitute these ligands by using allyl. So then there is another way to prepare metal allyl complexes. That is, you can take sigma allyl complexes, where the allyl ligand essentially forms a sigma orbital in the allyl ligand binds to a metal center, and that is why we call them as sigma allyl complexes. Unlike the pi allyl complexes with eta 3 coordination mode, the sigma allyl complexes, or in case of sigma allyl complexes, the allyl ligand uses 1 carbon atom to bind with the metal center, and that is why it is an eta 3 eta 1 coordination mode it has. So you can take eta 1 sigma allyl convert and then convert them conversion to eta 3 pi allyl complexes. So there are several examples of such type of reactions, and we've discussed about these reactions where a sigma allyl complex can be transformed into a pi allyl complex. Then the third type of reaction essentially involved conversion of either eta 2 or eta 4 olefins or oligo-olefins or diolefins into eta 3 allyl complexes. So again we will discuss a couple of reactions where an polymetal olefin complex is essentially converted into a metal allyl complex. So let us look at the different methods of preparation of metal allyl complexes, which essentially uses these three strategies. So we see examples of metathesis reaction first, that is where we can substitute an labile ligand in a metal complex by an allyl ligand. So we can take metal salts and you can use main group organometallic allyl reagents. So examples, you can take nickel bromide and then react this with allyl magnesium halide, that is a Grignard reagent with allyl group over here, and we know that the Grignard reaction needs to carry out in ether medium, and this will essentially give you a nickel allyl complex in this way. So one can easily prepare such metal allyl complexes by using allyl magnesium halides as the reagent by doing this sort of metathesis reaction. So another example of this type of reaction, again you can take allyl magnesium halide and the acetyl acetonate ligand can be now substituted by the allyl ligand to give us this sort of metal allyl complexes. That is, cobalt allyl complexes can be prepared in this way. So then one last example of this type of metathesis reaction, one can take zirconium tetrachloride and then this will give us tetraallyl zirconium. That is, so this is how one can prepare diallyl, triallyl as well as tetraallyl metal complexes. That is, these are all binary metal allyl complexes. We see that there are no other ligands apart from the allyl ligand present in these complexes, and that is why they are binary metal allyl complexes, and these complexes are thermally unstable, and that is why one needs to do the preparation as well as isolation of these compounds are under low temperature only, or otherwise the products will decompose under the reaction conditions. So this is how one can prepare different metal allyl binary metal allyl complexes by using a metathesis reaction and using the allyl Grignard reagent, essentially with different metal salts. Now we have seen during our discussion on metal carbonyl complexes that one can take metal carbonyl anions and then when reacted with alkyl halide, it essentially give alkyl substituted metal carbonyls. And now this reaction can be modified, or one can take allyl halides and react with carbonyl metalates, and that will also give metal allyl complex. The way it gives metal alkyl complexes when we react metal carbonyl anions with alkyl halides. So one can start with metal carbonyl anion. So manganese is in -1 oxidation state in this compound, and then one can do reaction with an allyl halide instead of an alkyl halide. So now we will have a sigma allyl complex. So the one of the sigma orbital of the allyl ligand will essentially bind with the metal center over here. So we'll have formation of a sigma allyl complex. Now this is a sigma allyl complex, but we see that the pi orbitals of the allyl ligand are not used to bind with the metal, and instead an sp hybridized orbital of the allyl ligand binds to metal center, and that is why we call it eta 1 sigma allyl complex. So this is eta 1 sigma allyl complex. Now, such complexes may undergo rearrangement from sigma allyl to pi allyl complexes, and this can be triggered by heating the reaction, this intermediate complex, or even by photoirradiation of this intermediate complex over here, which will release one of the carbonyl group from here as the pi cloud of the allyl ligand comes and attack on the metal center. One of the carbonyl ligand has to be released. So -CO, and the allyl sigma allyl complex eventually turns into a pi allyl complex to give this sort of a product to us, a pi allyl metal complex. Now in this case the manganese is now oxidized from -1 to +1 oxidation state, and in the product over here also it is in +1 oxidation state. So what we see, this is a reaction where sigma allyl ligand gets transformed into a eta 3 pi allyl complex. So by sigma pi allyl rearrangement reaction essentially. So then we can also see other type of reaction, other reactions of this type, where photoirradiation of a sigma allyl complex essentially produces a pi allyl complex. So we can take this molybdenum 0 metal carbonyl complex. So this is 0 oxidation state. So the complex is essentially negatively charged because one Cp ligand is present. And now one can do reaction again with benzyl magnesium bromide. So that is PHCH2 MgBr to give a metal alkyl complex first. So the metal alkyl complex is formed first. Now the complex is going to be neutral here, as a benzyl ligand is present over here, then one of the CO group can be released here, and this benzene pi cloud will come and attack on the metal center to produce a metal allyl complex. In this way, so molybdenum is in class 1 oxidation state in both in the intermediate complex over here as well as in case of the product. So again, what we see, a sigma allyl complex is rearranged into a pi allyl complex in this case, and in this case the release of CO that is triggered along with the rearrangement of sigma allyl to pi allyl complex is essentially triggered by the photoirradiation of this intermediate complex over here. So we have seen two different examples of reactions where a sigma allyl complex is essentially transformed into a pi allyl complex, and this during this reaction, one of the ligands attached to the metal center is essentially again released so that a coordination site is available in the metal complex for attack of the pi cloud of the allyl ligand to the metal center. So then let us look at other types of reactions for preparation of metal allyl complexes, and in this case a metal hydride, a reaction of a metal hydride with diolefin also produces a metal allyl complex, and during this reaction also a sigma pi allyl rearrangement takes place, where a sigma allyl complex is essentially transformed into a pi allyl complex. We'll see one example where a metal hydride, that is cobalt carbonyl hydride, during its reaction with butadiene produces two metal allyl complexes. In one case, this is CH3, and the other one so this is anti isomer and this is syn isomer, and both these isomers are formed during this reaction of this metal carbonyl hydride with diolefin. Now this reaction also, as we have said, that proceeds through a sigma pi rearrangement, pi allyl rearrangement step. That is, during the first state, hydrocobaltation takes place. That is, the olefin will undergo hydrocobaltation here, and it will produce a metal alkyl complex in this way. So one of the carbon atom get attached to the Cobalt center, one of the terminal carbon atom gets attached to the Cobalt center, while the other terminal carbon atom over here, the hydride ligand comes and attack over here, and that is why we call it hydrocobaltation reaction, and you produce this sort of sigma allyl complex here. This is sigma allyl complex. And now this complex again will undergo rearrangement by releasing one of the carbonyl ligand attached to the metal center, and then it is going to produce both these anti and syn cobalt allyl complexes. So we will now see examples of reactions where an olefin ligand the olefin complex is essentially transformed to a metal allyl complex. So one example of this type of reaction essentially involves reaction of metal salt with olefin in presence of a base. So first a metal olefin complex is formed, which is then rearranged into a metal allyl complex. So example of this sort of reaction is essentially if you take tetrachloro-palladium complex over here and then do reaction with a olefin in presence of a base, this will give us a dinuclear palladium allyl complex in this way. So two allyl ligands are attached to the palladium metals. So this reaction again, this reaction proceeds first by formation of a metal olefin complex, and which then gets rearranged into a metal allyl complex. So let us look at how the reaction proceeds by taking a simple allyl ligand. So this is an allyl ligand we see, and this is one of the hydrogen atom attached to the terminal carbon atom. Once this reacts with PdCl4 2 negative, one of the Cl attached to the metal center will be replaced by the olefin ligand to form a metal olefin complex. So this sort of metal olefin complex is formed first. Then this hydrogen atom will get attached to the palladium center over here, and this will produce a metal hydride complex, and during this process the allyl ligand will the olefin ligand will get transformed into an allyl ligand. So that is again one of the Cl will get replaced. So Pd Cl Cl and this hydride gets attached to the metal center. Now HCl will be released from this intermediate complex over here. This is negatively charged, while this is neutral over here, and once HCl gets released, what we will have is a dinuclear palladium complex containing the allyl ligand in this fashion. So that is how this product is formed. First, a metal olefin complex is formed, which then gets rearranged into a metal allyl complex, and then dimerization takes place by release of HCl from here to give us this resulting product. So this is another type of reaction that we have already mentioned, where a metal olefin complex, that is in this case it's a eta 2 olefin complex, gets transformed into a metal allyl complex. Now we will see examples where a metal diolefin complex, that is an eta 4 metal olefin complex, is transformed into a metal allyl complex. We have already discussed about this type of reaction during our discussion on reactivity of metal olefin complexes. We have seen that electrophilic adhesion reaction can take place in these metal olefin complexes. That is, electrophiles can come and attack on the one of the olefin carbon atom. If we use strong acids, so the H plus will come and attack on one of the olefin carbon atom, and this essentially transforms the olefin into a allyl complex. So let us see one example. So if you take, so this is metal diolefin, electrophilic attack on metal diolefin complexes. You can say electrophilic attack metal diolefins. So if we take this diolefin complex and then do reaction with HBF4, strong acid, we know during such reactions the eta4 ligand get transformed into a eta3 ligand, because so one coordination site is now available on the metal center, and to compensate for this coordination unsaturation we need another 2 electron donor. So if we have to use another ligand, that is a carbonyl ligand over here, and in that case now the diolefin will essentially get transformed into a allyl ligand, and this sort of a complex. So the complex is going to be positively charged here because we have added H plus over here, and this sort of metal allyl complex is formed by when electrophilic attack on metal diolefin complexes takes place. So we have already seen examples of such reactions during our discussion on metal diolefin complexes. So we have also seen that in case of such metal diolefin complexes also undergo nucleophilic addition reaction with alkyl lithium reagents, and during such process as well the nucleophile, that is the alkyl group, come and attack on the olefin carbon atom, and this produces once again metal allyl complexes. So we will see one example of such reaction where a nucleophile that is comes and attack on the olefin carbon atom and transform it into a metal allyl complex. So if you take this molybdenum complex, that is a CP ligand, that is a butadiene, ligand is coordinated in this way over here, and then the complex is positively charged over here, and then if we use alkyl lithium reagent, the alkyl group will come and nucleophilic attack on the olefin carbon atom is going to take place, and this will now transform into an allyl ligand in this way. So the complex will become neutral now because the alkyl group has come and attacked over on one of the olefin carbon atom in this fashion. So again we have seen how one can prepare metal allyl complexes starting from metal diolefin complexes either by electrophilic addition or by nucleophilic addition reaction. The diolefin ligand essentially gets transformed into an allyl ligand. Now we will discuss about two other procedures for preparation of metal allyl complexes. In one of these cases, hydrogenation of complexes with excess electron is carried out. So complexes with excess electrons may undergo hydrogenation so that they become, now they follow the 18 valence electron rule. So one such example of complex with excess electrons is this nickelosine over here, which contains 20 valence electrons. If you count, nickel is at the 10 groups, so there are 10 electrons from the metal center and there are 10 electrons from the two CP ligands, so total 20 valence electrons are there, and this complex may now undergo hydrogenation in presence of sodium amalgam in ethanol medium. So one of the CP ligand will undergo hydrogenation. One of the CP ligand, that is the custody metal center, will undergo hydrogenation, and this will essentially transform this CP ligand into an allyl ligand in this way, because the two of the carbon atoms over here have now become saturated, and the pi cloud is essentially localizing only 3 carbon centers here, and that is why it can be considered as a allyl ligand now. So this is how, so nickel is now oxidation state has now increased from 0, plus 2 to plus 1 over here, degrees from plus 2 to plus 1 over here. Plus 2 only again, because the Cp is minus 1 as well as the allyl ligand we can consider it to be minus 1. So this is one of the approach for preparation of metal allyl complexes, which does not necessarily fall into the category that we have discussed earlier. Then one final method for preparation of metal allyl complexes is transformation or coupling of allyl that take place in presence of metal carbonyl complexes, that is dimerization of allyl. So you can take Fe2CO9, and when you do reaction with allyl undergo dimerization. This carbon atom gets attached to another carbon atom from another allyl group, and this leads to dimerization of the allyl. And these allyl groups now get attached to the iron centers in this reaction. So this is how a dimerization of allyl take place, and the essentially a biallyl ligand is formed, which then gets coordinated to the iron centers in this complex in this way. So that is these are the different methods for preparation of metal allyl complexes, and this essentially brings us to the end of this lecture. We have discussed about different preparative methods for synthesis of metal allyl complexes, and what we have seen is that mainly 3 different strategies are used for preparation of metal allyl complexes. That is, the first method is essentially involves substitution of a labile ligand by a allyl groups by using a allyl magnesium halide as the reagent, and during this process a binary metal allyl complexes can be prepared, and we have discussed that such binary metal allyl complexes are thermally unstable, and that is why these metathesis reaction needs to be carried out only at very low temperature, or otherwise the complexes are going to decompose. Then we have seen that one can prepare metal allyl complexes by using doing a rearrangement of sigma allyl complexes into pi allyl complexes, and different approaches have been used for this purpose. In one of the method, we have seen how one can prepare metal allyl complexes by starting from carbonyl anions, carbonyl metalloids, and doing reaction with allyl halides, and this essentially produces a sigma allyl complex, which then gets transformed into a pi allyl complex by a release of one carbonyl ligand. And then we have seen that one can also start with metal hydrides, and these metal hydrides will undergo reaction with diolefins to produce metal sigma allyl complexes, which then gets rearranged into again pi allyl complexes by release of carbonyl ligands once again. So then we have seen how one can prepare metal allyl complexes by conversion of olefin complexes into allyl complexes. We have seen that metal salts, reaction of metal salts with olefins in presence of a base essentially produces metal allyl complexes via this uh, conversion of metal alkene complexes into metal allyl complexes. Then we have also seen how electrophilic or nucleophilic attack on metal diolefin complexes can result in metal allyl complexes. And finally, we have seen two other methods for preparation of metal allyl complexes. In one of these methods, a, a metal complex with excess electron is hydrogenated and that produces metal allyl complexes under the right conditions. And then we have seen how one can do dimerization of allyl um, eh, by using metal carbonyl complexes, and during this process a metal allyl complex is again formed. So let me conclude this lecture with this. I thank you very much for being with me during this lecture.